Okay, welcome back to the series where we cover reaction engineering. Okay, and this video is just going to be a foresight. All right, let's get that out of the way first. It's going to be a foresight. What does foresight mean? Why don't you just copy that in Google and find out, okay? This is going to be a foresight of what's to come in isothermal reactor design. Okay, reactor design. I hope all of you by now are aware of what isothermal means, but I'm gonna write it anyway. Note, it means temperature. There are no changes in temperature. So to make it even more formal, everything that has a d, every equation that has a d of t term will already go to 0. So there are no variations with temperature. All right, isothermal reactor design. And by foresight, I mean I'm gonna go over all the steps. In the upcoming videos, we shall explore each and every one of these steps one by one. Okay, and just so you guys can all follow, I'm still using Elements of Reaction Engineering as a textbook. Elements of Reaction Engineering by H. Scott Fogler, and the one that I have is the 5th edition. Okay, the one that I have is the 5th edition, and you guys can follow along. So this is even before chapter 1. This is like a intro. Well, we already had an intro. This is more of a to get you guys warmed up for what's to come. So we're gonna briefly go over the algorithm of isothermal reactor design. Okay, there we go. So let's see, and by algorithm I want to point it out, since this is an algorithm, you're gonna be using this over and over again, using it over and over and over again. All right, that is why these calculations are so repetitive that they can be mapped in an algorithm. So just every single isothermal reactor design problem can be easily tackled via this approach. This is just, and again, this is just a foresight. All right, let's start. Oops, my tablet is not being very friendly right now. I'm sorry. So let's start. All right, where do we begin? As a chemical engineer, you're always, well, 9 out of 10 times, you're going to begin by writing a general mole balance. A general mole balance on a species. Okay? And which is just going to be accumulation equals in minus out plus consumption, plus any sources minus any sinks. And yeah, that is the general mole balance. You're going to start off by writing that on your species of interest. And this is covered in chapter 1. Chapter 1 of your textbook. All right. And then you shall move forward to what kind of reactor do you have? Reactor configuration. What is the configuration of the reactor that you're dealing with? All right. And in this course, the options that you're gonna have: a batch stir tank reactor, a batch stir tank reactor, STR stir tank reactor, CSTR, a continuously stir tank reactor, a PFR, a plug flow reactor, and a packed bed reactor. A packed bed. We haven't talked about packed bed reactor before, but just to give you a little preview, the packed bed is just a cousin. It's just a cousin of a PFR. So if you know how to deal with PFRs, you can easily deal with packed bed reactors, also known as PBRs. Here we go. So that's our second step. What sort of reactor? And my tablet is not being very kind today. I'm sorry. And we'll make it work. Don't worry. That's not going to stop me. So this is going to be chapter 2. Because once you have the general mole balance and the reactor configuration selected, those are going to be updated. Your mole balance is going to be updated based on, all right, the mole balance is going to be updated and revised based on the kind of reactor you select. All right, and we're going to go over that in detail. So next up, we're going to need the kinetics. Okay, we need the kinetics, and these are usually found in your textbook. These might be given in the problem. You might need to go to an ACS published journals, an ACS published paper, or the Royal Society of Chemistry, the one that's in England, I believe, Royal Society of Chem. But for the most part, in this course, like for all the textbook problems, the kinetics are probably going to be given to you anyway. Okay, and I believe this is yes, this is covered in chapter. It's a cross between chapter 2 and chapter 3. Okay, chapter 2 and chapter 3. It's going to be the bridge between both of those chapters. And once you have the kinetics, you need to write an equation, a rate law expression. What do I mean by rate law? Let's say you have a plus B goes to C reaction, a very simple reaction. Okay, now in most cases the rate at which A is disappearing, the units are moles of A divided by liters times the second. The rate at which the concentration of A is disappearing is proportional to the reactants. And this is not going to be, and warning, this is not going to be the case every time, not going to be the case all the time. Okay, sometimes we'll have some really weird nonlinear kinetics, as we'll explore. So the rate law, once you have the rate law, you need to formulate a rate expression that you can enter in your code. All right, so just to give you a quick recap up till so far: start, general mole balance, what's your reactor configuration looking like, kinetics, find that, probably it's already given to you in your textbook, or you might need ACS or Royal Society of Chem journals, because that's where all the kinetics are usually recorded and published. You might even need to do experiments. You might sometimes need to do experiments, so we'll just add that here as well. Experiments, a bench scale experiment. All right, and this step shall be covered entirely in chapter 3. Yeah, chapter 3. Okay, next up, you'll have to use stoichiometry. What do I mean by stoichiometry? Suppose you already know our A plus B goes to C reaction. You know that the rate at which A is disappearing is going to be equal to the rate at which B is disappearing, and that is equal to the rate at which C is appearing. So just stoichiometry, you have to keep track of if certain species consuming, other species are being consumed as well, and the products are being generated. Stoichiometry. Okay, and next up, you have to make a decision. Is there pressure drop? Is there pressure drop? Okay, let me just make that is there pressure drop? All right. This one was chapter 4. Okay, chapter 4. Now you need to decide whether you have pressure drop or not. Let me zoom out a little, sorry. So if your answer is no, then solve. We're going to explore solution strategies as well. You can solve, some systems might be solved analytically, and some will be solved numerically, depending on the configuration, depending on the type of differential equations we get numerically. Okay, So if you have no pressure drop, then Bob's your uncle, go ahead. Beautiful. If you have pressure drop, then first off, no need to worry. I know some chemical engineers are really gonna dread pressure drop in their system. Pressure drop it's usually due to friction, due to a high friction factor. It's due to the presence of packing material. So yeah, pressure drop is basically a momentum transfer problem, presence of packing. So this is basically a momentum transfer / fluid mechanics problem. Fluid mechanic / momentum transfer. If you've taken a fluid mechanics class, then you've had some exposure to it. If you've taken a transport phenomena class, you've gone over momentum transfer probably. If not, that's okay. We're gonna make do with what we have. So you need to use a suitable pressure drop equation. That's gonna be an additional equation, a suitable pressure drop equation. And this shall be explored and both of these are gonna be explored in chapter 5. All right, chapter 5. And once you have the pressure drop equation, solve again, either numerically or analytically. Okay, I can't spell today, my bad. Analytically or numerically. And there you have it. There you have it. Every single isothermal reactor design that you will ever come across. And let me make it even more clear. Isothermal ideal reactors. There are going to be non-ideal reactors as you go to more advanced level. So each and every isothermal reactor design. Let's zoom out a little. Start. General mole balance. Done. What is your reactor? You've figured that out. Do you know the kinetics? Well, you'll find them. You'll find them eventually. A plus B goes to C. You formulate an equation. Well done. Well done. Good job. Good job. And if you know if 1 mole of A is being consumed, 1 mole of B is gonna be consumed, and 1 mole of C is gonna be generated. Some gen chem. Good job. Good job. And yeah, pressure drop. Well, pressure drop is gonna be scary at first. It's gonna be very scary, but we're gonna make some sense out of this chaos. And there you guys have it. Thanks for your kind attention, and I hope this was helpful.